Welcome. We'd like to take a look at solving a system of equations, again using Gaussian elimination and back substitution. However, in this case, we're going to find that there's no solution. We can find that there's no solution in the same way that we did previously, when we have a false statement. If I say 3 is equal to 0, well, of course 3 is not equal to 0, and it doesn't matter what I plug in for x, y, and z. 3 will never be equal to 0. So we would say there's no solution. All right. What I'd like to do is I'd like to work towards finding that, but the process is we start by applying Gaussian elimination. So I'm going to get rid of these three variables, get rid of x here, and y here to get that triangular form. So I'm going to take equations A, B, C. I'm going to eliminate the x's from equation B by subtracting equation A. Equation A stays the same as 3x minus 2y minus z is equal to 7. Equation B is the one that I am manipulating. 3x minus 3x gives me no more x's. Y minus a negative 2y is going to be y plus 2y, so that's 3y. Negative 3z minus a negative z is negative 3z plus z, so negative 2z. 2 minus 7 is negative 5. Equation C stays the same as 12x minus 2y minus 8z is equal to negative 5. Now, I haven't said this previously, but I'd like to point out that we perform one manipulation at a time. I don't want to manipulate equation B and equation C at the same time. I could, and it wouldn't be too big of a deal. The problem is that as we look to perform multiple manipulations at a time, I find that there are often errors in doing so. So one thing at a time to minimize the number of errors that are made. Hopefully none, right? All right, equation C I would like to manipulate. Again, relabel as A, B, C. I'm going to subtract, let's see here, 4 times 3 gives me 12, so I'm going to subtract 4 times equation A. You'll notice that I didn't bother having a leading coefficient of 1 or a coefficient of 1 on the x here because I was able to observe initially that I could use the value of 3 here to eliminate the x's and eliminate the x's. Equations A and B stay the same as 3x minus 2y minus z is equal to 7. 3y minus 2z is equal to negative 5 for equations A and B there. C is the equation that I am manipulating. This minus 4 of those eliminates the x's. Yay! This minus 4 of those is negative 2 plus 8, giving us 6y. This minus 4 of those, all right, so negative 8 plus 4 is going to give us a negative 4z. And this minus 4 of those, let's see here, make sure I get this right here. Negative 5 minus 4 times 7. 4 times 7 is 28, so negative 5 minus 28 should be what, a negative 33? Negative 5 minus 28. That sounds good. All right, relabel as A, B, and C. I can eliminate the y here by subtracting 2 of those. So take equation C and subtract 2 times equation B. Equations A and B stay the same as 3x minus 2y minus z is equal to 7. And 3y minus 2z is equal to negative 5. Equation C is the equation that I'm manipulating. 6y minus 2 of those eliminates the y's. Negative 4 minus 2 of those eliminates the z's. So I actually have 0 on the left-hand side. We're starting to think that, hey, maybe this is infinitely many solutions again. 0 is equal to 0. Except for negative 33 minus 2 of those is negative 33 plus 10, which is a negative 23. And 0 is not equal to 23. Uh-oh. So it doesn't matter what I plug in for x, y, and z. There is no solution. That would be the appropriate conclusion in this case.